Hello and welcome to another review session for the final exam in Calculus 3208 presented by CDLI, still underneath the large umbrella topic of derivatives, and today we're going to talk about differentiability and what that means. So in words, I can quickly say that if something is differentiable, it means it can be differentiated. In other words, you can take its derivative. And when we're differentiable and when we are not differentiable is sort of our topic for today. So what we're going to do is a little bit more formally, we're going to define differentiability. So right here we're going to talk about what differentiability really is. Then we're going to do a few things to try and understand what it is that can create for a function not to be differentiable. And then we'll look at some examples of some types of places where a function can't have a derivative, and we'll be able to recognize those. And then we'll do some examples sort of focusing around that last little bit. Okay. So let's get right down to it. So basically a function is differentiable if we can compute its derivative. So we have two types of differentiability. The first type is differentiability at a point. So basically we say that a function is differentiable at a particular point if its derivative, f prime of a, exists at that point. Or in other words, now remember we define the derivative in terms of a limit, difference quotient thing. So if this limit exists, then we can say that we are actually differentiable. And a lot of textbooks will say that. It's sort of correct. But there is one circumstance under which this limit can actually exist, but we don't really have a derivative. And we'll look at that in a few seconds. But then we're going to define differentiability on an interval. So if some function f of x, if we can take its derivative everywhere between x equals a and x equals b, so on the whole interval from a to b, then we say that it's differentiable at every point in that interval. So we have differentiability at a point, we can find the derivative at that point. Differentiability on an interval, meaning we can find the derivative anywhere on that interval. All right, so let's see if we can understand why we would or wouldn't be able to differentiate a function or find its derivative. So let's look at two examples here, and we're going to look first of all at the function f of x equals x minus 1 squared plus 1. So that's your standard parabola, shifted over 1 and up 1. And we're also going to look at f of x is the absolute value of x minus 1 plus 1. So that's your regular old absolute value function, shifted over 1 and up 1 as well. So these are two very similar graphs. We don't get any negative values on them. The only difference is the absolute value function has got linear behavior, whereas the parabola has got that quadratic behavior. So we get straight lines versus curves. And let's see what kind of a difference that can make here. Okay, so we define differentiability as the ability to take this limit, and we're going to have to be able to take that limit from the right and from the left. So this is not very clear, but that should be a plus for taking the limit from the right, and this should be a negative for taking the limit from the left. All right, so let's think about this for a second. Remember how we first came up with the idea of the limit that we use to find derivatives? Well, it was all about taking secant lines to estimate the slope of a tangent. So here's one particular secant line that's drawn, and then we try to improve our estimates by making the secant line have the 2 points where it touches the curve get closer and closer together, etc. So a way to think about this limit as we approach from the right is if we choose our second point, where we're going to draw our secant line other than the point of tangency, to be a point that's to the right of the point of tangency, then we'll sort of follow that curve as we make that, or follow that secant line as we make that point get closer to the point of tangency, and we'll see what happens to our graph. And what we can see is if we take this point right here and move it down and down and down, then these secant lines are going to get flatter and flatter, and eventually what we would end up with, and we can see the idea, is that we'd get a horizontal tangent line across there. So if we're approaching from the right, everything seems to work pretty smoothly there. So we could say that, and we're not doing this in a very technical way, we're just sort of getting a concept here at this point. This is the understanding part. But we can say that as we come from the right, this limit would have a value of 0, because that seems to be where we're headed. Now if we come from the left, it's really the same story, except that we're choosing points to the left of the point of tangency to make as our second option for our secant line. So there's the first point we could choose, and that one. And then what we'll end up doing here is we'll end up choosing a bunch of those, and as we choose that point to get closer, those secant lines will flatten out eventually, and we can see that what we have here is once again a horizontal tangent as everything levels out. So it looks like the limit as we approach from the left would be equal to 0. So that example is a good illustration of a way that our left and right limits would be the same, and so we are actually differentiable at that point. Okay? Let's look at this next example, and we'll talk about what's going to break down here. First of all, we'll look at what happens if we come from the left at this one. So let's left, and this one's going to be from the right. Okay, so coming from the left, no matter what point I pick on the graph of g of x, which is this absolute value business, no matter what point I pick over here for my first option for my secant line, I'm only going to get the same secant line as any other point I could possibly choose. So it doesn't really matter. This is like finding the limit of a constant here. All of my secant lines will have the same slope, and no matter how close I move that point, I'm still going to get that same slope. And they're all going to have the same as the slope of the curve that's on that side, which is -1. So coming from the left there, that particular function would have a slope of -1 if we looked at the limit. Coming from the right, we'd have a similar situation, but we'd get the opposite thing happening, because no matter where I choose that point for my tangent, or sorry, for my secant line over on the right, if I shrink these down to get them close to there, it's not going to make any difference. And this time, all of my secants, as I would evaluate my function, would give us a slope of 1. So the limit of all of that would have a slope of +1. So coming from the left here, I have a slope of -1 all the time. And coming from the right, I have a slope of +1. So my limits don't agree. So we would say that we're not differentiable at x equals 1. A little bit of a kind of a fancier way to think about that, or less fancy way to think about that, I should say, is let's just look at the top graph here. Let's say I wanted to try to draw a tangent line at that point where x equals 1. Well, if you remember, one thing we should know about tangents is that they are unique. There's only one tangent that can touch a particular curve at that point of tangency. There's only one real one. So if we look at this and I try to draw a tangent line, I could draw it like that and I'd only touch the curve at one place. Or I could draw it like this and I'd only touch the curve at one place. Or I could simply draw a horizontal line and I'd still only touch that curve at one place. So all of those things could be possible candidates for the tangent line. And because we have so many different things happening there, we can't find a derivative because there is no unique tangent. So that's not differentiable. That's not the only type of function that gives us non-differentiability, though. Let's take a look at some other options. And there are really three what we call usual suspects here that can cause our differentiability to break down. And the first one we have there is a corner. I wouldn't particularly, in my language that I use to talk about calculus, call that a corner. Your textbook does, but I would call this when the curve is sort of bent upward from both sides. I call this a cusp point, C-U-S-P. A corner point I usually think of more as like the absolute value, where I've got two straight lines coming together, as straight as I can possibly draw a line anyway. But in this case, it's kind of for the same reason. If you think about trying to draw a tangent line at a cusp or a corner, then we're not going to have that uniqueness property. I could get multiple different tangent lines happening there. So that's not differentiable at that point. So at x equals a there's no derivative. There's no value at all. And if I look at the next one, it says it's a discontinuity. And there's good reason for that. If I try to approach from the left here, I might get one particular slope. And if I try to approach from the right, I might get something different, or I might get the same. But in the end of the story with this one, where in the heck do I draw a tangent line if my graph is disjointed like that? So do I put my tangent up here? Or do I put my tangent down there? Or do I put it this way? There's no way to draw a tangent that really makes any sense for that. So this is an important thing to note. If a graph is discontinuous, then that means that the function is not differentiable. So that's an important thing, because if we know that a function is differentiable, then that would tell us it must also be continuous. So that's an important point for us to make. It's not a huge concept, but it's an important thing. We say that differentiability is what we say implies continuity. So if you know that you're differentiable, there's no way that could have happened if you weren't continuous. So we say differentiability implies continuity, but just because you're continuous, continuity doesn't necessarily imply differentiability. So it doesn't work the other way. These are converse statements, and converse statements don't necessarily have to be true. And in this case, one of them is not. They don't have to be logically equivalent. So just because we're continuous doesn't mean we're differentiable. And the two graphs on the left and right here illustrate that. The first one is continuous at A, and so is the second one. But we're not going to be differentiable at either one of those places. Okay? So let's look at the last one then. And in this case, we have a vertical tangent. And I mentioned earlier in this video that it's kind of a weird thing. It's possible for that limit to exist and still not have a derivative, and this is the case I mean. If that limit exists, but the limit has a value of plus or minus infinity, then, well, you don't really have a derivative because the infinity as a value itself is undefined. It can be a limit, but it's not a number. So there's no value for the derivative on a case like this one, because we know that it's a vertical tangent line. And if we have a vertical tangent line, what that means is we have an undefined slope. So if we have an undefined slope, then we also have an undefined derivative. So we're not differentiable here. So that can't work. So three cases we have to look out for: corner or cusp, discontinuity, or vertical tangents. And be careful about that relationship between differentiability and continuity. One can imply the other, but it doesn't work in the opposite direction. Alrighty. Here's an example, and it says for this graph, we have to list all the points where the function is not differentiable. This poor function looks like it's been through the war. And then we have to give reasons for each one of those points. So if we look at all the different places, so we should recognize on this one that this vertical asymptote we see right here, that's going to break down our continuity issue. So what we see then is that x equals -1. That's our first point we're going to mention, that we're going to be not differentiable. And if we have an asymptote, that means we're going to be discontinuous. So if we're discontinuous there, so we have a discontinuity, that means we have no derivative. Okay? The second place we can see here is where x equals 0, so right along the y-axis. And again, we've got this jump discontinuity happening here. And if we have a jump at x equals 0, then again, for the same reason, we have a discontinuity, so there's no way we can have a derivative. And for the last one, this is the case where we have that weird corner cuspy thing going on, and I just can't draw a tangent line there. So that's at x equals 2, and at x equals 2 we're also not differentiable because we have that corner, also known as a cusp, if maybe your teacher called it that. Okay? So let's move along. Not much to all of that. Here's a multiple choice question that came from a test, and it says, which is true of the graph of f of x shown? So the limit as x approaches -1 is what's written here. It's a little bit hard to see that, but what's down there is actually just x approaches -1. And this one is the limit as h approaches 0 of f of -1 plus h minus f of -1 all over h. We should recognize that what that is the definition of the derivative. So that's the derivative of this function, f of x, at x equals -1. So let's see. That first limit, so that should be an easy one to evaluate. The limit as x approaches -1 of f of x. Does it exist or not? And that'll narrow down our options here. Well, that's an easy thing to evaluate. If I come from both sides, is my graph approaching the same place? Absolutely. So this guy over here should be okay. So these two does not exist options are eliminated. Then we're going to look at the second one. And once you recognize that this is in fact the derivative, the problem becomes a lot easier because we know this is a cusp point. No tangent's going to work there, so we're not differentiable. So this thing up here, this is not going to exist. So while the limit does exist, the derivative does not, so this guy can't be an option, and our answer here has to be C. Okay? So that's a way to try to throw a little curveball at you for one of those type questions. So here's the your turn question, and on this question, you're given a graph, and just like we did with a similar one earlier, you have to determine the two, oh, I'm not going to give that away, all the places on the graph where we're not differentiable, and give a reason why based on one of those three criteria that we had for non-differentiability. And I'll put up the solution now. So here's the solution, and of course there are just two, and there they are. And last but not least, we're going to do a quick summary of all the stuff we talked about in differentiability here. So stuff about differentiability: a function f of x is considered to be differentiable whenever its derivative, or the limit that defines it, exists. But be careful with that limit when it comes to a vertical tangent. There are three main reasons why a function fails to be differentiability. So we know that one is a corner or a cusp point, second is a vertical tangent, and the third is a discontinuity. And when a function is differentiable at every point in a given interval, we say it's differentiable on that entire interval. So that's pretty much everything you need to know about differentiability in Calculus 3208. Happy studying.